The laws of reality, as we know them, fundamentally rely on the principle of balance. Energy can neither be created nor destroyed. What goes in must come out. To the 17th century Italian physician Santorio, exploring this balance within the human body led to a decades-long period of self-experimentation. For 30 years, he weighed every liquid and solid that went into his body, and every liquid and solid that came out. He weighed his body before and after a variety of physical exertions, day in, day out, matter in, matter out. Confusingly for him, his excretions failed to measure up to the mass of his food and drink. It was as if a campfire had been burnt to ashes, the wood used as fuel weighing far greater than the grey flecks left in its place. But Santorio believed the missing matter had to have gone somewhere. It could not just cease to exist. And by the end of the 18th century, natural philosophers would definitively demonstrate Santori's base assumption was true. The total amount of mass before and after a chemical reaction was equal, whether it was the human metabolism breaking down food into smaller molecular units of fats, proteins and sugars, or the woody fibers in a campfire's fuel releasing carbon dioxide and water as it burns. Each chemical equation is balanced, an equal number of each kind of atom at the start of a reaction and at the end. They merely rearrange themselves into new substances. But the very light of day showed us this kind of balance is not always true. In the 20th century, when scientists unlocked the nuclear power of the atom, it was revealed that the total amount of mass could indeed change. Deep within the core of our Sun, hydrogen becomes helium, but the total mass involved in creating this helium is greater than the mass of the helium itself, and no other matter exists on the end side of the equation. It appeared unbalanced. But a famous equivalence put forth by a young Swiss patent clerk showed that mass only needed to be reconsidered as part of the total energy of a system. The difference in mass is converted into energy, a photon, sunshine. Balance restored. But what would happen if there were an inherent imbalance to the universe? Our bodies, our world, entire galaxies billions of light years beyond the Milky Way, nearly everything we can reach out and touch consists of matter. However, there is another kind of matter out there, a near-identical twin. We call it antimatter, and there is almost none of it left. An obvious, enormous imbalance stretching out across the cosmos. Yet without this imbalance, we would not, and could not, exist at all. Not a single person, not a single planet, not a single star. Where did this imbalance come from? How is the observable universe packed so densely with matter, with its partner almost entirely absent? And why did the vast cosmos seem so perfectly balanced at its inception, yet just not quite? This video is sponsored by Magellan TV, the documentary streaming service. Question: when the Sun dies, what planets will it consume? A. Only Mercury. B. Mercury and Venus. C. Mercury, Venus and Earth. That's right, either B or C. Scientists can't be sure. As the Sun expands into a red giant, it will grow and pass Venus, but Earth may just survive. And so, our recommendation this week is the documentary Solar Superstorms 4K, a fascinating exploration of what exactly the Sun shoots at us, how it affects our daily lives, and how it could lead to severe consequences. Magellan TV are a sort of Netflix for documentaries, with more than 3,000 videos to choose from on a wide range of topics. And History of the Universe viewers can take advantage of a special holiday offer. Buy one, get one free gift cards for an annual membership by clicking the link in the description. The most famous relationship in all of physics is often cited to be the one between mass and energy. E equals mc squared. C is representative of the ultimate speed limit for anything travelling through space, and equal to that of light if it is travelling unencumbered through pure nothingness. As simple as it appears to be, this equation provided a fundamental basis upon which Einstein's laws of relativity could stand. In the early years of the 20th century, the world was being ushered into a new understanding of reality, where strange things happened at speeds and scales unfathomable to the human mind. Albert Einstein was merely one of many brilliant minds revealing how the extremities of our universe defied common perception. And so, just a few years before Einstein rewrote the laws of nature, Paul Dirac was born in Bristol. First a student of engineering, he transitioned into mathematics, earning a PhD from Cambridge in 1926. Incredibly precise, both in thought and word, tales of him sleeping during lectures would end with his waking to offer a quick and clever retort to the speaker. His advice to fellow physicist Niels Bohr, known for his plentiful drafts of papers, was that you should never start a sentence without knowing the end of it. And from his postgraduate years and beyond, Dirac's research obsession lay in a brand new area of physics. In 1925, quantum mechanics had rewritten our perspective of the subatomic world. Particles, though the only ones known at the time were the proton and electron, could simultaneously exist and be described mathematically as waves. By 1926, Erwin Schrödinger had published his keystone equation for quantum reality. But Dirac noticed it was incomplete. It didn't account for the effects of Einstein's relativity. Someone needed to tackle this problem. Diving into the math, Dirac soon discovered an incredible secret hiding within the relationship between energy and mass. E equals mc squared was wrong. Or rather, like Schrödinger's quantum model, it was incomplete. Merely reflective of one specific situation when a massive particle is not moving relative to its observer. This difference is only significant at extreme speeds, yet these speeds are reached at the imperceptibly tiny scales of electrons orbiting their atomic nuclei. As Dirac pieced together a more universal quantum understanding, he obtained an updated, more complicated equation, which later bore his name. Many years later, he was asked how he found the Dirac equation. It was said he responded, "I found it beautiful." But what did this discovery actually mean for the energy and mass of our universe? Up until this point, electrons had only been allowed to have positive energy. But within the math of this incredible breakthrough lay a surprise. They could also have negative energy. But this created a problem. In the 1920s, physicists knew that electrons always sought to exist in the lowest possible energy state. If negative energies were possible, as Dirac's equation suggested, this would mean that zero energy was no longer the lowest level. There should be an infinite number of negative energy states to fall into, with every electron throughout the universe constantly spiraling downwards and downwards into negative infinite energy, emitting infinite amounts of light in the process. But of course, that was not, and is not, the case in our universe. For his equations to make sense, Dirac needed something to block the electrons. He needed those negative energy levels to already be taken. And so, this infinite well of negative energy electrons was known as the Dirac Sea. Under Dirac's hypothesis, a negative electron could occasionally get a boost of energy, such as through a collision, and become positive, the whole would mathematically act exactly like an electron, but instead have the opposite amount of electric charge. Initially, Dirac thought this could be the proton, discovered 30 years earlier, with its positive charge. But protons are roughly 2,000 times more massive than an electron, and thus didn't fit the bill. So Dirac reinterpreted his physics. Instead of a proton, he decided it was an anti-electron. It was 1931, and Paul Dirac had proposed antimatter. But physical proof was still needed. The light of distant stars is not the only thing streaming across the universe. Particles with mass do too. Cosmic rays, mostly composed of lonely protons, continually rain down on the Earth's atmosphere. Some are created by our own Sun as part of its solar wind. Others may hail from the supermassive black holes at the center of distant galaxies. In 1931, Carl Anderson began his studies of cosmic rays using a remarkable box which could track these minuscule particles' movements. A cloud chamber. An airtight box filled with water vapor. When a cosmic ray particle streams through the chamber, it causes nearby water molecules to condense into liquid. This creates a visible trail which provides clues about the cosmic ray's properties. Cloud chambers had been used for 2 decades, but Anderson had improved upon the design and identified a new trail which appeared identical to those made by electrons, but mirrored. Particles that had the same mass but opposite charge. He had discovered Dirac's anti-electron, and so in 1932 Anderson published his results and gave the first antimatter particle its name, the positron. Dirac's sea, however, was not long for this world. Over the decades, alternate theories about the fundamental quantum behavior of particles would take its place. But Dirac's antimatter had been proved real. However, for scientists to discover other antiparticles, they had to turn their eyes from the sky to their own experiments. In massive particle accelerators, powerful magnets direct charged particles in loop after loop, until they reach intense speeds. When those particles are finally directed to collide with a target, some of the energy in the collision converts into an equivalent shower of massive particles, including particles too unstable to be found elsewhere in the universe. Since positrons were already relatively rare in cosmic rays, it would take a huge amount of patience to detect heavier antiparticles. They decided it was far more efficient to create their own. And in 1955, inside the Bevatron accelerator at Lawrence Berkeley National Laboratories, scientists created and discovered the antiproton. A year later, they had revealed the antineutron. However, it would take another 4 decades before accelerator technology was advanced enough to construct an entire anti-atom. At the low-energy antiproton ring at CERN, antiprotons flew around their magnetically constructed ring 3 million times a second. Each time around, they flew through a field of xenon gas. Occasionally, the energetic interaction between an antiproton and xenon atom would spontaneously create an electron-positron pair, and in an even rarer event, this new positron could be taken up by the antiproton, finally settling into an atomic orbital. And in 1995, after a 3-week-long experiment, 9 anti-hydrogen atoms were crafted. Nearly 2 decades later, CERN scientists were able to study the properties of anti-hydrogen, specifically how it interacted with different wavelengths of light. These experiments demonstrated that anti-hydrogen acted exactly as regular hydrogen would have, and to all intents and purposes, scientists believe that antimatter behaves almost identically to normal matter. An antimatter particle would have the same mass as its matter counterpart. An antimatter star burn just as bright. Which, impressively, was exactly what the work of Paul Dirac had proposed, nearly 90 years earlier. Imagine a world where humanity could harness the power of antimatter. What do you see? Do you see massive interstellar starships barreling through the cosmos, expanding our reach to habitable worlds beyond our own? Do you see extraterrestrial colonies braving harsh or Eden-like environments peppered with alien life, staring out at two setting suns? Or do you see desolation, the aftermath of a technology untamed, a power station explosion that dwarfs Chernobyl and Fukushima, humanity's worst traits leading us to mutually assured destruction? Either of these outlandish fates would arise from matter-antimatter reactions being the most fuel-efficient process in all of known physics. Through the relation between mass and energy realized by Einstein over a century ago, 100% of the mass in a matter-antimatter annihilation is converted into energy in the form of light. Gram for gram, a reaction between matter and its antimatter counterpart releases over 100 times the energy in nuclear reactions, and 1 billion times greater than what is released when burning fossil fuels. There is no process in all of physics which can do better. These days, antimatter batteries, engines and warheads are the realm of science fiction. Far more energy is shared in the creation and storage of antimatter for scientific study than is actually stored within the antimatter's mass, and thus unusable as fuel. And though one day our descendants may leap over these hurdles, you don't actually need to imagine a distant future or a bizarre alien world to interact with antimatter. In 1940, the Canadian chemist Martin Carman was working at the Berkeley Radiation Laboratory at the University of California. His goal was straightforward by description: create a brand new version of a very familiar element. Carbon, the backbone to all life as we know it. Carman sought to create a new isotope with hopes it could be used in medical research. Working day and night, going multiple nights without rest, he and his colleague Sam Rubin would irradiate samples of graphite, hoping the reaction would convert some of the pre-existing carbon isotopes into new ones. And on the 27th of February, he finally took a break. Stepping outside the lab, sleep-deprived and dishevelled. But the fresh air would soon prove a little too exhilarating. A patrol car passed by the lab. The policeman inside noticed his appearance and took him away. Not for violating the rules of fashion, but because he was suspected of murder. It turned out a convict had escaped a local prison and gone on a killing spree. Carman matched the man's description, but was eventually cleared and free to return to his graphite samples. And it was within those samples he finally uncovered what he sought. He and Rubin had created carbon-14. This isotope is rare in nature, but now is famous for its use in radiocarbon dating, through which scientists can measure the age of an object containing organic material, whether it be human, animal, or plant. And this is because for every trillion carbon atoms in your body, one is carbon-14, and when you die, you stop acquiring it. Unlike the rest of the carbon, which was forged in the heart of a star before our own sun was born, most carbon-14 came about much more recently. While it is oxygen gas that provides us the breath of life, our atmosphere is mainly composed of nitrogen, and occasionally, in the skies above, cosmic rays will strike a nitrogen atom, creating carbon-14. This carbon-14 combines with oxygen, creating carbon dioxide, which is then incorporated into plant life through photosynthesis. And finally, it arrives to you. As you go about life, you continue to acquire new carbon-14, keeping the total ratio of carbon-14 in your body constant. But at the moment of your death, a new clock starts. The carbon-14 decays with nothing to replace it. The ratio drops. And scientists can use that ever-changing ratio to measure how long ago it was when a living thing stopped accruing more carbon. When it died. And this decay process within the atom is another example of the universe seeking balance. Known as beta decay, While carbon-14 decay turns a neutron into a proton, two other particles have to be created: a free electron and a ghostly antineutrino. As well as this, as the potassium-40 in your body decays, it occasionally takes an inverted path, creating a positron instead of an electron, and a neutrino instead of its antimatter counterpart. In either situation, or rather by both combined through the mild radiation of these two elements, you and all life on Earth are natural antimatter factories. And that is just one way in which antimatter is involved in our day-to-day lives. Indeed, in the 1950s, scientists began researching ways to harness antimatter for medical imaging. If a radioactive element could be safely injected into the human bloodstream, the circulatory system would distribute it throughout the body. As the element decays, it releases a positron. The positron quickly finds its matter counterpart, an electron, and annihilates, creating two photons with a specific amount of energy. A machine capable of detecting that energy signature would then be able to map where in the body the annihilation happened. This was the positron emission tomography, or PET scanner. They are used not just for the detection of medical disorders, but also to discern what parts of our brain are responsible for performing certain tasks. Admiring a sunset, listening to a story, gazing at the stars. And, looking at those stars across the greater cosmos, we find yet more antimatter. It can be ejected by violent supernovas or the collision of dense, rapidly spinning stellar remnants called neutron stars. It has even been detected in massive jets of radiation being fired directly away from hungry black holes. In the 1970s, astronomers detected a cloud of positrons at the center of the Milky Way. And in 1997, NASA's space-based Compton Gamma Ray Observatory detected a veritable fountain of antimatter shooting 3,000 light-years out of our galaxy. The source of each of these is still a mystery, and we still don't know how much antimatter is out there, waiting for us to find it. And yet, despite its surprising ubiquity in our lives, the number of antimatter particles we have detected through the known cosmos is vastly smaller than that of all of the matter. A simple fact that we can thank for our existence and the continued existence of matter in the universe. But, as it turns out, this is a modern imbalance. It wasn't always this way. And turning back the clocks to the origins of everything, we find that for a brief moment at the dawn of the universe, things were very different. The first antimatter formed in tandem with the first matter. 1/trillionth of a second after time itself began flowing and our known universe came into existence, temperatures had cooled to a mere million billion degrees Celsius. There was energy, there was light, there were the fundamental forces that govern our reality. But there was no matter, no stuff of any substance. Upon reaching this temperature milestone and following the law of mass-energy equivalence, a soup of quarks and antiquarks arose from the sea of energy. Each single quark popping into existence alongside its antiquark twin. At the same time, gluons, the particles carrying the strong nuclear force, came into being. In a cooler world, they would have the power to bind quarks together, but it was still much too hot. These individual particles would zip around, randomly flying and colliding with one another. When quark and antiquark met, they would annihilate. Their mass returned to energy, 2 photons of light left to bound around in the quark-gluon plasma. A near total massacre of matter. Ever-growing, the universe cooled. Leptons and antileptons sprung forth in pairs. Electrons and positrons, neutrinos and antineutrinos, and so on. But such a decrease in temperature meant that new quark-antiquark pairs could no longer appear from the apparent vacuum of space. Those that remained were now slow enough for the available gluons to successfully bind them with other quarks, forming hadrons. Antiquarks would do the same with their own kind, forming antihadrons. The hadrons we know best are protons and neutrons, but other more exotic and less stable hadrons were composed too. Now, hadrons and their antihadron counterparts, protons and antiprotons, neutrons and antineutrons, could annihilate each other. And when the universe was 1 second old, the final matter-antimatter particle pairs were born of the universe's energy. With the seconds ticking away, the battle between matter and antimatter peters out. 100 seconds into all of history, matter wins, with 1 particle in a billion remaining. It is now cool enough for protons and neutrons to begin the process of nucleosynthesis, creating new elements for the very first time. But, according to what we understand about the Big Bang, the universe never should have had this chance. Matter and antimatter were created in equal amounts, thus they should have been equally destroyed. Our universe should have been set gloriously alight with photons from the total annihilation of all matter. Not a single atom left to see that light, let alone enough to form a star, or a planet, or you. So how can we explain this fundamental violation of balance in the universe? Scientists have some ideas. Perhaps some say there is an equal amount of antimatter out there, particles which were flung away from the war as the universe expanded, eventually forming anti-galaxies and anti-stars in distant regions. We know that the spectrum of an anti-hydrogen atom looks identical to that of hydrogen, so an anti-galaxy would be indistinguishable to our telescopes. But intergalactic winds would eventually carry regular matter into these anti-galaxies, and astronomers have yet to observe any light indicative of the resulting annihilation. Still, smaller antimatter objects, like clusters of anti-stars, could persist, going about their business for billions of years, with the antimatter they shed perceived as just part of cosmic rays. Signals lost amid the noise. But most scientists now agree that an even stranger reality may be the answer. That in fact, the universe may not, in the end, have the balance or symmetry we long assumed it did. Qiansheng Wu was born in 1912 in a small fishing town north of Shanghai. Unlike most Chinese girls at the time, she received a formal education, attending a school for young women founded by her own father. She graduated from a university in Nanjing at the top of her class with a degree in physics. After a few years of research, her mentor and fellow female physicist Dr. Jingwei Gu suggested that Wu emigrate to the United States to continue her education, and she received her PhD from the University of California at Berkeley in 1940. In 1944, she relocated to New York to join the Manhattan Project at Columbia University, and by the mid-1950s, she was nationalized as a US citizen and an expert in beta decay. And from that expertise, she was asked to push the boundaries of reality and rewrite our understanding of physics. The fundamental laws of nature, at first glance, appear symmetric according to 3 properties. The first property is charge. We are most familiar with electric charge associated with the electromagnetic force, positive and negative. Theoretically, under charge symmetry, the positively charged up quarks and negatively charged down quarks that comprise protons and neutrons should be identical in mass, and nuclear reactions should proceed identically if using a proton or neutron as instigator. The second is parity, often thought of as handedness, because your own hands display the very concept. No matter how much you rotate it, your left hand will never be the same as your right. It is only through the use of a mirror that you can turn one into the other. By itself, the notion of parity symmetry states that the universe has no preferred direction to anything. But charge parity, the combination of both charge and parity symmetry, dictates that if you were to put our universe through a mirror and replaced matter with antimatter, this new universe would look and act identical to our own. Should extraterrestrial life from that universe deign to visit us, our telescopes would be unable to reveal their composition until a first contact handshake resulted in our mutual destruction. And the third property is time. Time symmetry dictates that the laws of physics should operate the same if every particle suddenly found its direction, speed, and spin flipped to the opposite orientation, as if some cosmic hand was hitting the rewind button on the remote for our universe. Together, these principles make up CPT symmetry, upon which our fundamental understanding of reality is based. But what if these principles were very slightly broken? In 1956, Chen-Ning Yang and Sung-Dao Lee, the latter also at Columbia University, proposed that parity, or handedness, was asymmetric, particularly in the processes governed by the weak nuclear force. Before publishing their controversial paper, Lee approached Dr. Wu to ask her if anyone had designed an experiment to test parity, offering two ideas of his own. She proposed a third. The experiment she suggested relied upon a radioactive isotope of cobalt, cobalt-60. It is a synthetic compound, created in particle accelerator labs, and decays by creating both beta rays, the electrons created in beta decay as with carbon-14, and gamma rays, which are high-energy photons. In Wu's experiment, these atoms were constrained within a magnetic field and cooled to extremely low temperatures. One by one, the unstable nuclei would undergo beta decay. As charged particles, the electrons created would be directed along the magnetic field lines in one of two directions, upwards or downwards. If parity was conserved, there would be no preferred direction for the electrons to go. The ratio of those going up and those going down would be equal, including when a mirror universe was simulated by flipping the direction of the magnetic field. But this is not what Wu's team found. Instead, a greater number of electrons preferred to go against the direction of the magnetic field, no matter how it was oriented. Nature differentiated between left and right. Parity was broken, and the universe, at its most basic level, was not symmetric. Unfortunately for Wu, her teaching duties required her to return to New York during the experimental period, and she was absent on the day the first groundbreaking results came in. It was December of 1956, and Lee quickly spread news of these preliminary results to other scientists, who within weeks would confirm the asymmetry Wu's team had observed was true. And yet, when the 1957 Nobel Prize in Physics was awarded, it went only to the two men behind the theory. Irrespective of this possible Nobel snub, Dr. Wu is today remembered as a figurehead of nuclear physics and a key contributor in revealing the universe's asymmetry. But all this work was just the beginning. Further Nobel Prize-winning experiments in the second half of the 20th century not only confirmed Li, Wu and Yang's results, but also violated CP symmetry, the combination of charge symmetry and parity. By the end of the 20th century, it was definitive, and multiple scientists had shown that quarks and antiquarks were being treated differently by the laws of nature. The universe was fundamentally, in an extremely small way, out of balance. And so, could this be the reason why matter ended up outnumbering antimatter? As of now, scientists believe the answer is no. At least not entirely. When adding up the collective contribution that quark-CP asymmetry could play in the overall makeup of the universe, scientists realized the effect was not enough to produce the 1 in a billion asymmetry between matter and antimatter, which arose in that first second of time. So where else must we seek? It may be that other particles are also treated differently than their antimatter counterparts. Current research is investigating CP symmetry in the other family of fundamental matter particles, the leptons, and preliminary results are promising. Another source of the universe's matter-antimatter asymmetry may be caused by there being another type of neutrino, which only existed at the birth of our universe. Neutrinos are cosmic phantoms which barely interact with other matter and have a mass of almost zero. Around 100 trillion pass through your body every second, having almost no effect. And yet, despite this ghostly nature, they may have been a key factor in the early battle between matter and antimatter. The proposal arises from an unbalanced quirk in the neutrinos we observe today. Just like human hands come in both left and right-handed versions, all particles in the standard model can be described as having a left-handed or right-handed version. This is true for both matter and antimatter, and scientists have observed both left and right-handed versions of every particle, except the neutrino and antineutrino. Instead, every neutrino scientists have studied is left-handed, and every antineutrino is right-handed. If right-handed neutrinos are revealed not to exist, it could mean that neutrinos are their own antiparticle. Or if right-handed neutrinos do exist, the majority of them decayed long ago. So if neutrinos do not operate under CP symmetry as early results suggest, these right-handed neutrinos could have had a preference for what they decayed into. They could have decayed into matter more frequently than antimatter. Will this be enough to get us to that 1 in a billion? It is too soon to say, for now. Indeed, the results may prove similar to that of quarks, the asymmetry being insufficient. But even then, all is not lost. It may still be that there are pockets of antimatter out there, never having made contact with the rest of the universe, making the true ratio of matter to antimatter even smaller. Perhaps, one day, a floating slab of antimatter could appear on the horizon and give us our answer, before annihilating the entire Earth in a blinding flash of light. Indeed, aboard the International Space Station, a special detector is on the hunt for the antimatter version of a helium isotope, anti-helium-3. By revealing how much antimatter can be detected in our own cosmic backyard, within the air encircling our own cosmic house, we might be able to extrapolate this abundance to discover how much is out there, and how matter truly won the war within the first few minutes after the Big Bang. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.